In this video, we're going to look at the key components of good data visualization. That is, we're going to look at the fundamental elements of a data visualization that will let you effectively tell the story that you want to communicate from the data. First, we're going to look at the most useful elements for encoding quantitative data in graphs. Now, the principles I'm going to present are based on the science of human visual perception of information, mainly as elaborated and compiled by Stephen Few, who is one of the world's leading experts on data visualization. So there are some elements of data visualizations that we see here that good visualizations would bring together to compose into a graph. The first element is a point. And a point means some sort of dot, or it could be an X, or it could be a little shape, but that is placed in two-dimensional space across an X and a Y axis that has meaning in its position relative to both axes. Next are lines, and lines essentially connect points, and the connections between them the points might remain or might just be the connection, the trend of the connections, which are represented by lines. And lines work when there is a meaningful order in the progression of one point to another. Next key element is a column, a vertical, or that can be a vertical column or a horizontal bar, which work more or less the same. And the key item here is that there is meaning encoded from the 0 point, which is at the edge of one axis, to the limit, where the relative length of the bars proportionally indicate where each column or each bar and the size of each column or bar in respect to each other. So that's another key component. And the last key component to note are boxes. And boxes are quite special. They are used specifically in what type of visualization, a box plot. And they are used to represent distributions in a special coded way, where the lower point of a box is the lowest point in general of the distribution. The highest point is the highest value in general, and the midpoint represents a medium or average point, usually the median. It could possibly be the mean. And there might be outliers, larger or smaller values that go outside the boxes. But in general, a box represents visually the range of the distribution of a value, and at the same time indicates the midpoint. So these key elements are the components from which effective visualizations are built. And there are other components which are widely used, but which unfortunately are not so effective in encoding data. And we're going to look at some of these. So the fundamental principles of good and bad chart types. First, good chart types use these elements that have just been presented. They are composed of these. So again, the science of visual perception indicates that these elements are those that represent data, especially numbers, but not only numbers, in a way that intuitively matches both what humans understand easily and can accurately represent the reality underlying those numbers. In contrast, bad chart types, and bad is a stark word, but I'll go into some detail. Bad chart types use features to encode information such as areas. That is the area or volume of size of an element indicates the relative size. Bad charts might use angles, where the differences in angular difference, larger angles mean larger values, smaller angles, smaller values. And bad chart types also use 3D on a 2D surface. A 2D surface such as a screen, like here, this is a 2D screen, or they might print them on paper and they try to represent 3D. And these are chart types that do not work very well. Okay, so let's look at some of these challenges. First, bars and columns are very effective as long as they start from 0. So in this first chart on top here, you have the different sales amounts of different products, some software products. And here you can see MicroStrategy is on top, and it looks much better than all the rest, except when you look at the axis. The axis starts from 60% going to close to 85%. And this wrongly gives impression that MicroStrategy is doing, I don't know, about 8 times as well as the weakest player, Cognos PowerPlay. But if the bar chart is properly displayed here, where everything starts from 0, and the exact amounts are even specified here, you find that the difference between the best MicroStrategy and the worst is only around 20%. It's nowhere near as dominant an advantage as what the initial chart shows. So this is misleading, and bar charts should always start from 0, so that because the relative length or width, the relative length of the bars or columns work the same way, should represent the full amount. Another point is when expressing time in a chart, the time variable should always be on the x-axis. And the time variable might not necessarily be in specific dates. It might just be in a sequence. Like in this chart, which is the standard format, you have plant height over time. And there you have the occasion that plant height starts low over time and then increases more rapidly, and then it kind of tapers off in the speed. However, the same information could be expressed with time in on the y-axis and height on the x-axis. But this gives the impression that it starts off fast and then goes medium and then goes fast. And the problem with this is that this just violates a convention. People expect that time is displayed on the x-axis. And whenever you don't follow that convention, there's a miscommunication there because it's against what people expect. So this is purely conventional, but convention is a very big part of human perception and human understanding. So do not violate a convention like this, otherwise you will give people the wrong information. Perhaps a more controversial point has to do with using areas or angles to express quantitative or numeric differences. By far, well, one of the most common ways of this is using area charts of some sort to represent differences in size. So very often larger circles might represent more size than a smaller circle. But to give an illustration of the problem with this, let me ask you, obviously this big circle is larger than the small one. If the small one is unit size 1, how much larger is a big circle than the small circle? Just take a moment and guess. Well, the big circle is exactly 16 times as large as a small circle. I would guess that probably most people did not have 16. Most people probably thought it was smaller than that. And that's just because of the way people perceive information. And sometimes people might encode this information as 4 times larger, or where they're just using the diameter as the measure. Other times it might be appropriately used as area, 16 times larger. Is very confusing. Bubble charts, which use size and of area to differentiate some quantitative measures, can be somewhat used in the sense that if you want to show that one item is bigger than another, bubble charts do show that. But if you want to show how much bigger, bubble charts do not work. So please take care of that. Just know that bubble charts can show relative differences, but for precise indication of the differences, they just don't work. Now, another challenge here is using angles to try to encode differences. And this is very common with the ubiquitous pie chart. So just looking at this, for instance, which is the largest segment from A, B, C, D, E, and F? They look pretty even, right? All around. But actually, they're not even. There are differences between them. And this is because it's very hard for us to tell differences in angles when angles are very close to each other. For one, it feels like half the space and the others are smaller. It's easier to see those big differences. But for fine differences, pie charts just do not match the way people can easily perceive information. So some people try to improve this by maybe making it 3D. And this is even worse because now the ones that are seem closer to us seem even bigger, and the ones farther seem smaller. But it does not, we cannot trust that impression. A much better way to represent this kind of information is to use a simple bar chart. And with a bar chart, you can not only see clearly that there is a ranked order, and you can very easily tell which one is larger and which one is smaller, but you can, well, this one is well labeled where you can see exactly what the amounts are, or at least you can see on the scale. So one principle here is that in almost every case, a bar chart will represent the same information a pie chart is trying to do much more intuitively, much more accurately. And note that this bar chart is deliberately grayscale in contrast to the colorful pie chart, but the bar chart is far more informative, even without colors. You could add colors to liven things up, but that doesn't add to the informativeness of this simple bar chart. Another concern is with stacked column charts. So on the bottom here, you have standard column charts where each column has its own individual column is separate. But in stacked column charts, the different values here, we're looking at sales regions, west, east, north, and south. In the stacked columns, they're all stacked in one column. And the one on the left, everything totals up to 100%, and you see the relative amounts. And the one on the right, they're distinguished by quarters, and the quarter amounts are represented in sales. Now, the challenge with stacked columns is that it's very hard to get precise estimates. And that's because even here, well, these numbers are not so close, so it's not too hard to see that west is largest, but east and north, which one is larger? It's very hard to tell here. And when you have multiple stacks here, again, it's very hard to compare region to region, quarter by quarter. However, a stacked version of these, you can tell that ever so slightly east is higher than north because column charts do represent quantitative information accurately. The very slight differences are perceptible, and they do indicate slight differences in value. And when you break it down here, you can more easily see that the different, you can see the differences within a quarter, and you can see where there are differences for each region within the quarter. Now, stacked columns can be partially useful. I wouldn't say that they're never useful. They do have some benefits. Where they do not have a benefit is when the total is 100%. So the differences between the items are purely internal. These really do not add anything. In this case, separate columns are pretty much always superior to a stacked column. However, when you have this situation, when you break it down by some criteria, in this case by quarters, and the unit is not by, well, the main thing here is not breaking down by quarters, but the fact that the unit is not 100%. It's not percentages, but it has some meaningful unit, in this case, US dollars, or thousands of US dollars. Because here, with the different stacks, you can see that which quarter is the highest. Because it turns out that these taken together, if you don't look at the internal values of the stacks, these are essentially column charts. And here it is by quarter. You can tell that the fourth quarter was the best, and the third quarter was slightly better than the first. And that carries information which is not conveyed in this clustered column chart, because here, although you can compare within quarters, it's not very easy to see which quarter overall had the largest amounts. So this is one example where stacked columns, again, because the total is not 100%, if the y-axis totals were 100%, it would not be able to distinguish between the quarterly sales. Because they are actual amounts, this can be a useful visualization. The last principle I'd like to talk about here is maximizing the data to ink ratio. The data ink in a visualization, and this applies not only to graphs, but even to tables, is the ink or in the color or the text or the words that actually encode data. So here in this table is the words, departments, the exams, the header information, the actual data in the columns, the summaries. There's information conveyed there. In the graph, including the axis labels that show the amounts of each level, the legend that tell the meaning of the data, the columns and the colors of the columns. This is the ink, and each element of this has information about the data. This is the data ink. The non-data ink, in contrast, are aspects of the visualization that do not have actual data, but they support, enhance, or highlight the data. In these visualizations, the non-ink data, well, here are these bars in the table that separate the header rows from the actual data, and also separates the summary information from the actual data. They tell that these are not actual data, it distinguishes them. So that's non-data ink. And in the graph here, the only non-data ink are these lines that separate the axes from the data within the actual graph. So that is what is called non-data ink. A fundamental principle in good visualizations is to strive to use the minimum non-data ink possible so that the data ink is most visible. So reducing the non-data ink is just anything that's not absolutely necessary, that does not help understanding, get rid of it. And for the data, the non-data ink that remains, in this case, separating the headers from the data is important. Separating the axes labels from the actual data in the graph is important. So this needs to be de-emphasized and as little as possible should be used. And that makes for an effective visualization. Now, for the data ink, the data that actually conveys information, anything that is not essential, remove. So any data that is not part of the story you want to tell, get rid of it. Any data there should be essential. And if there is some data that is most important to you, then emphasize that. So for example, in this particular graph, the direct sales in blue are a stronger color than the indirect sales. So they draw more attention, and that is the story that wants to be communicated. So these are various principles that hopefully can help you towards developing better visualizations by understanding the core components, which when brought together can lead to effective data visualizations.